We're going to continue with a focus on geometric series and sum of the series, but we are looking at a very specific case. It is the case which we had in the second example we just did, where our ratio was less than 1. A funny thing happens when the ratio is less than 1. An interesting example is assuming you have a frog sitting in the middle of a circular pond, and let's say it's sitting right in the middle, and the radius of the pond is 1 meter, and let's assume this is our imaginary frog which has no width or height or any dimensions, so it's a mathematical frog, and the frog is trying to get out of the pond, and it leaps half a meter, except every time it leaps, it loses so much energy that it can only leap half the distance it hopped before. So that would be a quarter, and that would be 1/8, and the next one would be 1/16, and so on. So the question is, will it ever get out of the pond? And if every time it's hopping half the distance to the edge, we'd expect it never to get out. So it's going to get really close, but not actually get out. So all of these leaps are adding to a unique value, being 1 meter, but it will never actually get there. How do we deal with that in maths? Well, we refer to that as limit. Limit of his approach is 1 meter, and then we assume that that limit is the value that we get. So if you look at the previous example, my ratio was 1/3, and 9 plus 3 is 12. 12 plus 1 is 13. And then becomes 13 1/3, and then the next term being added is 1/3 of 1/3, so 1/9, and the next term is 1/3 of 1/9. So every time I'm adding a tiny bit to it, until the tiny bit I'm adding is so negligible that it can't be even perceived. And so if you saw, my limit was 13.5. Again, going back, I had 9 plus 3, 12, plus 1, 13, and then that formed my 13, and the rest became limited to 1/2. So what's happening here, and how do I derive that equation? So let's look at the formula we have. Sn a 1 minus r to the power of n over 1 minus r. A is fixed, it's not going to change, and n is that idea of leaping forever and ever and ever, and it's called limiting sum. So to this formula, as n approaches infinity, so we're looking for that final limit of the limit right at the edge, what happens to r to the n? Well, since r is less than 1, well, it's actually between -1 and 1, so let's write absolute value of r is less than 1. I'll just write the example to the power of n. Then r to the n will approach. What happens as n approaches infinity? This becomes 1 to infinity over 3 to infinity. 1 to the power of anything is 1. 3 to the power of infinity is even a bigger infinity. 1 divided by infinity is going to be 0. So r to the n is going to approach 0. So as n approaches infinity, since my ratio is less than 1, r to the n is going to approach 0. So my formula becomes s infinity a 1 minus 0 all over 1 minus r. Or S infinity is equal to A over 1 minus R. And that's the formula for limiting sum. Let's look at a quick example. Well, let's do the pond one. The pond one, the series was the frog hops half a meter, then half of that, then half of that, and so on. So my first term is a half, my ratio is a half, and I want sum to infinity. What's the limit as I add infinite number of terms? So the rule says sum to infinity is A over 1 minus R. A is a half, 1 minus a half is a half divided by half is 1, which is what I expected to get. That covers all the content that's the basis of, the processes of working with arithmetic and geometric series. Until the new reference sheet came on board, which has all these formulae on them, the HSC questions were straightforward. They asked for find the first sum of the first however many terms, or what's the 10th term of this series. But since these formulae are given to you now on the reference sheet, those basic questions are no longer asked in the question in the HSC, and the HSC questions are based on application of arithmetic and geometric series. And the next series of videos will look at various types of application of these two series in different areas, specifically for geometric series in finance.